I hope everybody who has gotten a chance so far has gotten their test back. I'll ask you to wait until the break if you haven't yet, just so that we don't have people sort of like walking in front of the thing. Right, so some quick stuff before we get into the test stuff. Exercise 7 is up now. These are derivations and predicate logic, and all of these involve skills that we haven't learned yet. So if you looked at these last night and thought, oh my God, I don't know how to do any of this, and not only it involves stuff we haven't learned yet, it's stuff we won't learn until Wednesday. So there's 2 more rules we're going to introduce on Wednesday. So would you mind waiting? Thank you. Thank you. OK, so because you're not going to get the skills to do any of these until Wednesday, the due date is extra extended. So it's extended well after, it's after reading week. Next week, by the way, is reading week. Isn't that nice? Hooray. OK. So the due date is November 10th. So you have basically 2 whole weeks to do these ones. We will have all the skills in place by Wednesday. Enjoy your reading week. OK, questions about that? Yeah, I know. I gave you homework on reading week. I'm sorry. Sorry. You feel free to do it this weekend. But OK, so here's the test stuff. Let's talk about the test. So here's the overall, just to show you the overall scores. The average was 75%. The mean was 75%. And this is score versus number of students who got that score. So this is, I'm sorry, it's too small to read, but this is about 50%. This is about an A, and this is A+. I don't think anybody got 100%, which is suspicious. I suspect one of you that got like 99 will come to my office hours and show me that they marked it wrong. You are welcome to come and get 100%. That's fine. OK, so that's the overall average score. Truth tables and validity, you guys knocked these out of the park. Average of 86 on this. So this is 1 to 8 in the number of students who got that. Symbolization was more of a bell curvy sort of curve. This is the average was 68 on the symbolization, so the mean was somewhere in the 12 to 13 range. Yeah. And derivations, the mean was 77%, more of a wide distribution on the derivations. People did all levels of goodness with a particular peak at destroying them. So there was a goodly number of people who just absolutely cleaned out the derivation section, but for the rest of us, there was a sort of reasonable distribution amongst the different scores. OK, so many of you have questions. That's fair. Here's what I propose to do. I'm going to hold special office hours today from 1 to 3 in my regular office. Please come talk to me about anything, any questions you have about this test. You're absolutely welcome there. You're absolutely welcome at my regular office hours, which are on Wednesday. So 4 hours this week where you can come ask me questions about, hey, why did I get this mark? You should also very much be checking our math. I've had 3 people so far report math errors on their tests. So I am responsible for having added up the numbers on the back page. Those are my errors and inputting all the data. I did not crack open the tests and check the TA's math within those sections, so you should do that as well. OK, so if there's a math error that's real easy to solve, you just show me your test, and I will fix it for you. My apologies. I don't think I can just answer. I don't think I can answer questions like, please don't swarm me right after class and show me your test, because immediately after doing 2 hours of lecturing is the worst time for me to be thinking carefully and delicately about your question. Let me get some food in me, and then I will have a fair and even-minded response to your question, if that's OK. OK? Questions about the test or any of this stuff? Yeah? What's the location? What's my office. My office. It's on the syllabus. Yeah. JHB 538. Yeah. Yeah. Other questions? Other questions not of the form, why did I get this score on this question? I know undoubtedly there are a lot of those, and I want to answer them, but I can't do that right now. Yeah?
Will the correct answers be posted?
We can do that, but you should know that all of the correct answers won't be posted. There will be a subset of the correct answers. If you provided an answer that you believe is correct that's not posted, then you should talk to me, especially if you didn't get marks for it. Yeah. So I can post my grading rubric, which basically says these are what I think are right answers, plus you should give them marks for anything else that's right. So that process might not have been perfect. You know, when you're marking 300 tests, you're not going to get it right every single time. So, other questions about this stuff? Okay. Good. So let's move on to derivations in predicate logic. This is your intro to derivations in predicate logic. So today I'm going to introduce to you 3 new rules. On Wednesday there'll be 2 more, and that'll be basically all of the new rules for derivations in predicate logic. So, I mean, we had what, like 10 rules or something like that before, including the derived rules, 10 or 12. So we're not adding all that much more technical machinery to our derivations skills. All of the old stuff, as I mentioned before, all of the old stuff from sentential logic is still in play here, so all of those rules still apply. You can still make all of those moves, and we're going to add the following 3. So that's the content of today. We're just going to go through these 3 rules and show how they work. Okay, so the rules are universal instantiation, existential generalization, and existential instantiation. Okay, so let's start with universal instantiation. So recall the meaning of a universal claim. Universal claim says, whatever I slot in for this variable, this sentence is going to be true of it. For anything you put in here, this sentence is going to come out true. So for all x, if hx, then gx, is equivalent to saying something like, if a is an h, then a is a g, and if b is an h, then b is a g, and for however many things are in your domain of discourse, however many things you're talking about. So that means that it makes sense, it's always going to make sense to do the following. To apply it to any name or any variable. So if you've got a universally quantified sentence, you can instantiate it to any name or any variable. That looks like this. So here's the rule in action. Suppose I've got this as my 2 premises, I've got this universally quantified sentence for all x if hx then gx, and I've got as a premise A has the property H. And I want to show that A has the property G. What I can do is say premise 1 UI, universally instantiate. And the quantifier falls away, and we just replace all of the instances of the variable with something. And that thing can be, with one small caveat, which I'll talk about later, can be anything that you want. And you can do this as many times as you want in the proof. So I can say premise 1 UI to A. Then, of course, you can just do the usual sentential logic stuff to this. You've got if HA, then GA. And you've got as a premise HA, therefore you get GA. You're done. Hooray. OK? OK. So that's universal instantiation in action. You can do this to names. So this is A is a name letter. You can also do this to variables. And there's nothing wrong with doing this to the same variable that you started with. So for all x, if hx, then gx, and you want to show gx, and you've got hx, then that's fine. You can universally instantiate for all x, if hx, then gx, in the form of if hx, then gx. Yeah? So this is because of the meaning of a universal quantifier. The universal quantifier says, look, I don't care what you plug in here, it's going to be true. So if you plug in a name, if you plug in a variable, it has to apply. If the universally quantified sentence was true, then it's got to be true of anything you want. Again, with one small caveat. And it doesn't have to stay, you don't have to keep the variable letter the same. You can switch it to a different variable letter. So you can get out of for all x, if hx, then gx. You can get if hy, then gy. That's fine too. It's lovely. Universal quantified sentences are great. You can pull all kinds of stuff out of them. And they don't get used up. So if I wanted to, I could just keep pulling stuff out of premise 1. I could say, if hb, then gb. If hc, then gc. If hz, then gz, and so on and so forth. You can continue to pull things out. It's always going to be a valid inference to say, look, if this applies to everything, then it applies to this thing, and this thing, and that thing, and the other thing. Yeah? Okay. Universal instantiation. There are a couple of restrictions on how you have to use this, however. So, just to say this again, you can UI to any variable with one exception or name, because a universally quantified sentence says for anything you put in this variable, the sentence will be true. It's why UI works the way it does. Now, the caveats, the restrictions. You can only UI to sentences where the main operator is the universal quantifier. What does that mean? That means that this doesn't work. This following inference does not work. So you've got a universal as part of the sentence, but not the main operator of the sentence. So I switched languages. Sorry, I didn't explain this. So we used to talk about the main connective of the sentence. Connectives are operators. Quantifiers are also operators. So if we just had for all x, if fx then gx, the main operator would be the universal quantifier. Does that make sense? You can only use this rule on things that are universally quantified sentences, not things that contain universally quantified sentences. Did that version work? Yeah. Well, that's an excellent suggestion. That's an excellent suggestion. You can just simplify. So now exactly what we've done here, but you do have to make that move. That's the point. So yes, you are allowed to do that, but you do have to make this move. You can't say, I'm going to universally instantiate line 5. You have to split off the universally quantified sentence, so you have it as the main operator. Right now, the for all x is the main operator of line 6, and that means I'm allowed to use UI on it. I'm not allowed to use UI on parts of sentences. That's all I'm saying here. Is that clear? This is just like with the rules in sentential logic, where you're only allowed to apply the rules to the whole sentence, not to parts of the sentence. Yeah? OK. Good. Another restriction on universal instantiation. So that was you can only apply it to the whole sentence. This is you have to apply it to every instance of the variable that's in the sentence. So here's what you're not allowed to do. If you've got for all x, if fx, then gx, you're not allowed to go to, so you've universally instantiated to A for the f part of it, but not for the g part of it. And that's not allowed. When you're replacing this stuff, you have to replace every single instance of it. So I hope this sort of draws out a little bit about why that might be true. So the first sentence says, the FA then GA says, if A is an F, then it is a G. That makes sense, right? So if the universally quantified sentence is true, all F's are G's, then you can infer validly from that if this thing is an F, then it's a G. What you can't validly infer from that is, if this is an F, then there is something that's a G. Because nothing restricts that X to being A in that sentence, so X is still a variable. So you're saying, if all frogs are good, and Alfred is a frog, then Alfred's good. Okay, good. All frogs are good. If Alfred is a frog, then there is some random X that is good. And X, we haven't said what X is. So we haven't justified that claim, right? And similarly, you have to instantiate to the same letter throughout. So you cannot do the third thing either. You can't say, for all x, if fx and gx, if y is an f, then x is a g. Hopefully that's super clear why that's not legit, right? So if this random variable has property f, that doesn't entail that this random property, this totally different variable, has property g, right? The first sentence only justifies you in saying the same thing that had the f has the g, right? So the reason why you have to place it in every single instance is so you're talking about the same thing, not giving yourself the conclusion that some other random thing has this property. Okay? Okay, hopefully it's clear why we're doing that. really just what you need to remember is the rule that anytime you universally instantiate to every instance of the variable in the sentence. Yeah? Yeah. Okay. Is that okay? Okay. So this is where remembering your scope stuff matters, right? So every instance of the variable under the scope of the quantifier must be replaced. So in this case, both of those x's are under the scope of the universal quantifier that's out front, right? So that means if we're going to instantiate, if we're going to UI to the sentence, or from the sentence to something, we need to replace all of those x's. And both of those would be legitimate UIs. Those are both fine. So in the first one, we replaced x with x. That's fine. In the second one, we replaced x with a. And so long as we hit every instance of it, we're fine. We've satisfied this constraint. Okay? But it's only the ones within the scope of that quantifier. Good? Okay, good. Okay, so to review, that was universal instantiation. It's a fairly straightforward, so using this rule is fairly straightforward, I hope, in its basic mechanisms. Seeing it in action will be slightly more complex, but really it's just you replace all of the instances of the variables with whatever you want, with one small caveat, and you only UI to the scope of the main operator of the sentence. So you do it to everything, you do it to only things that are universally quantified sentences. Okay? Okay. This is not an obscure rule. You will become very familiar with this rule as we go through. Okay. So that was universal instantiation. Now let's do existential generalization. So given a sentence that asserts that some specific object has a property, or that you can generalize from that to the fact that there exists at least one object with that property. What? Okay, that says, if I say Dave has long hair and a good job, which we could symbolize as LD and GD, yeah? So if that sentence is true, it must be the case that there exists at least one thing that has long hair and a good job. Right? Because we know that's true because Dave does. Yeah? So this is always going to be a valid inference. This is our rule existential generalization. And this is when you don't have a quantified sentence. So in the last rule is what's called an elimination rule. That is, you start from something with a quantifier, you end up with something without a quantifier. Here we're doing the opposite. We're starting with something that doesn't have a quantifier, and we're ending up with something that does have a quantifier. Yeah? So it's an introduction rule. We're introducing the existential generalization. Okay. Is it clear why this one makes sense? If I know a specific object with some properties, then I know that there's at least one object with those properties. And that's all the existential generalization says, right? All the existential generalization says is there's more than zero of this kind of thing. And if I have an example of that kind of thing, then you know for sure that there's more than zero of them. Yeah? Okay, now to the restrictions. Or sorry, no, we're not at restrictions yet. We've still got more we can say about this. So remember in the universal instantiation, remember that so long ago? You had to apply it to everything in the sentence. This one, that's not the case. Because look at this inference and tell me whether this makes sense to you. Dave has long hair and a good job. That's our premise. And now we say there exists something that has a good job and Dave has long hair. Does that make sense? It should make sense. Right? But we didn't, well, all we did here was just didn't generalize one of the variables. Or one of the names. We didn't generalize one of the names to a variable. We just said we're going to leave this one LD, we're going to leave that specific and allow the second half to be general. And that's fine. Because it's still true, right? If you know that Dave has long hair and a good job, you know that there exists at least one thing that has a good job, was Dave, and that Dave has long hair. Yeah? That should be fully convincing and transparent to you that one thing follows from the other. Okay? Okay. And of course, you can do the opposite. There exists something that has a good job and Dave has long hair. So when you're existentially generalizing, you can do all of the names to variables, or you can do one of the names to variables or the other, however many you want. Okay? Okay. Some restrictions on this. The existential quantifier must have scope over the whole formula. So this is what you're not allowed to do. If you've got HA or JA, you're not allowed to say there exists an X such that HX or JX. So you're not allowed to just pick half of the sentence for the scope to range over. The scope has to range over the whole sentence, even if you didn't include. So you could have done in this incorrect sentence, if you'd put brackets in it and you'd said there exists an X such that HX or JX, that would be fine. Or if you'd said there exists an X such that HX or JA, that would have been fine too. What you can't do is just selectively existentially generalize part of the sentence. Yeah? Okay with that? Okay. So here's the thing, the caveat that I kept mentioning. It's the no capturing rule. No capturing rule. And this applies to universal instantiation and existential generalization. So here's how they put it in the textbook. When using rule UI or rule EG, a new variable must not be introduced if some of its new occurrences are bound by a quantifier in the original formula. I'm going to say that a different way in case that's not super duper clear. This textbook is wonderful in the sense that it gives you like rigorous definitions of all of the relevant concepts, but they're not necessarily rigorous definitions that you can like use in your mind to understand things. So that is if you're like, what's the definition of the no capturing rule? That is our definition of the no capturing rule, and if you parse it out, then it'll always work. But here's a different way of saying that. So when you UI or you EG, you're introducing variables. And the rule is those variables must not already fall under the scope of a quantifier inside the sentence. So if you've got an embedded universal generalization, so here's an example. Here's an example of the no capturing rule and why this makes sense. So we've got this, we're starting from this large universal generalization that has embedded in it an existential generalization. Yeah? So says something like all jackals are hungry and there exist carrots, the kind of thing that you would say to your friends on a Saturday night. Okay, so that's all fine, right? That all makes sense? Okay. Now, what if I universally instantiated this sentence to Y? So I violated the no capturing rule by universally instantiating to a variable that already appeared inside the sentence. So Y already appeared in the original universally quantified sentence. Y was already appearing. And now I've universally instantiated to Y. And now what does the sentence say? It says, if something is a jackal, then it is hungry and a carrot. That's not quite right. Right? We all were happy with all jackals are hungry and there exist carrots. Well, I mean, not the ones that just ate, but that at least made some sense. And now we've said something totally nonsensical. We've helped ourselves to a claim that we know can't be true. The reason why that doesn't, yeah, question?
Sorry, I didn't mean to.
Oh, that's okay. Yeah.
So the Y,
Yeah.
these are all arbitrary?
That's right, yes. These variables are, so anytime you have a the question is, are these variables arbitrary? And yeah, anytime you have a quantified sentence, those variables don't pick out anything in particular until they appear free. So this is the difference between a free variable and a bound variable. If a variable is bound to a quantifier, then the variable name doesn't, the x or the y or the z or whatever it is, doesn't matter, right? You could replace all instances of it and it would be exactly the same claim. Whereas if it appears free, so the jy there is not bound to a quantifier, now we're talking about something. That y has to have if you're talking about y in one part of the derivation, you're talking about the same y in other parts of the derivation, anytime that you see y unbound to a quantifier. Okay? Yeah?
The first one, y hx bounded by the exist y.
Why is it?
Y is in the bracket of the extension of y.
In order to demonstrate the no capturing rule for you. Why did I, so it's a somewhat bizarre way of representing this sentence. It's kind of like, you probably wouldn't symbolize it this way, but I symbolized it this way in order to demonstrate this rule for you. Is that a satisfactory answer? Okay, okay. There's nothing wrong with that sentence though, right? That sentence is fine, the first sentence. It does say all jackals are hungry and there exist carrots. Okay? But if we allow ourselves to UI or EG to a variable that already is inside the sentence, then what we're saying is that two things are the same object when they're not necessarily the same object. Could be. It could be that if something is a jackal, then it's hungry and is a carrot. I'm not ruling that out, but we just don't know that yet, right? We have no reason to believe that given the first sentence, so it was an invalid inference from one to the other. That's why we have the no capturing rule. Yeah?
I'm just curious, where did the C come from? Like, what is the C symbol?
Oh,
Is it a
sorry, that should be, instead of K, it should be C. Sorry about that. Bah. You also might have been wondering where that K was. There you go. Okay, thank you. A murmuring goes over the crowd. I can't tell if you're piecing this out or if you're just doing something entirely other than logic right now. Yeah?
Is that correctly symbolized?
Is it? I hope so. Well, I clearly think so. Yeah. Yeah, I think so. Does anybody think there's a problem with the way that's symbolized? I'm not ruling it out, but yeah.
Yeah. From all jackals are hungry and there is carrots, the orders intuitively seem to get messed up when it gets translated to the first symbolized sentence.
Yeah, intuitively, yeah. So this is not how I would expect you to symbolize this on a test.
Is there another way?
Yeah.
For instance, would you be able to say the universal quantifier x, if jx then hx, and existential quantifier cy?
Sorry, I missed all that. I was trying to produce the answer. Hang on. Was that what you were saying?
No. Why would hx come after the existential quantifier? Why wouldn't it be before? Because you're first saying jackals are hungry, then you're saying there is carrots.
Okay, but the order in which you symbolize it does not have to match the order of the sentence. Remember with only if, we reverse things? Yeah, so the order in which you symbolize things does not have to match the order of symbolization. We're extracting the logical form from the surface grammatical form. Okay, but if you're asking, so this I think would be also a perfectly fine way of symbolizing this. It is not, however, an example I could use to teach you the no capturing rule. That's the only problem with it. Yeah?
So the consequent is that is the induction of the entire conjunction?
Sorry, in this version or the version I just had? So actually, the answer is both. The version I just had, yes, it is actually the whole consequent. So if we said the following, because of our blatant conditional bias, the conditional is always the main connective. So yeah. OK? OK, so that's the no capturing rule. What I want you to remember here is you don't universally instantiate to a variable that's already inside the sentence. You don't existentially generalize to a variable that's already in the sentence. Pick yourself a fresh variable. Yeah? Yeah.
If we were to go off the top and you kept it and then you plugged in y instead of x, but you kept there exists a y, c and c and cy.
Uh-huh.
So like, no.
Wait.
No, so go back to what it was before without the double brackets at the end. Yeah.
It's like that?
Yeah. And then you go again, so you follow through, you apply EG to that line, and you pick y as your variable. Would that be all right?
Whoa. We apply EG to what?
To that first line?
You can't EG that first line.
Or if you apply
UI, do you mean? Aha. So we're UIing to the first line there.
Yeah, and so you change the second line to remove that second bracket, just like you did on the first line.
OK.
Would that now be correct?
No, that's still not right. Still not right. It still says if something is a jackal, then it is hungry and a carrot.
Because doesn't the existential quantifier mean that if the y could be something else?
All right, it does. It does. Yeah, so in that case, you don't actually come up with a problem. Nonetheless, the no capturing rule says we're not allowed to do that. So the no capturing rule rules out some things that are actually logically OK. But for the sake of not running into problems when it's not OK, we say that you're not allowed to do that. Is that OK? Yeah. Yes, you're absolutely right. So in the second sentence here, because the y is bound to that there exists, it's in its own little scope. The scope of that y is just cy, so it's like a new variable. But so in that case, it's not a problem. But nonetheless, the no capturing rule still says you're not allowed to do this because we want to rule out the cases where it does become a problem. OK. OK. I'm sorry. Once again, this stuff is really weird and abstract when I'm just presenting it to you and you're just sitting there listening to it. When you see it in motion, this stuff will make a lot more sense. So we will get to some of that. All right. So just to review the existential generalization rules, unlike UI, you do not have to existentially generalize to every instance of the variable. You can be selective here. However, the introduced existential must have scope over the whole sentence. So when you run an existential generalization, what you end up with is an existentially generalized sentence, and the whole sentence is the existential generalization. So the product of this rule is always a sentence with an existential quantifier out front, and the whole sentence is the scope. Okay? You don't ever existentially generalize to just part of a sentence. The product of this is always the whole scope is existentially generalized over, and no capturing. That is to say, you're not allowed to existentially generalize to a variable that already exists in the sentence. And we saw an example where that's a problem, an example where that's not such a problem, but nonetheless is still ruled out by this no capturing rule. All right? OK. We've got one more rule to do. Do you want to break now, and then we'll do the third rule and some derivations, or do you want to do this rule and then have a break? Hands up for break now. OK. Break later? OK, that got a lot more hands. OK, let's keep going. So third rule, we'll introduce this third rule. We'll take a break. We'll come back, and we'll do some examples. Existential instantiation. So here's the intuitive version of this. If you have an existential claim, you're allowed to suppose that something instantiates it. Not some specific thing, some generic thing. So if you've got, there exists a dog who can read, you're allowed to say the following somewhat weird thing. There is some object, I, let's call it I, that is both a dog and that can read. This is just saying, okay. And then you can use I, this I elsewhere in your proof, right? So you can, the reason why, this doesn't seem to get you very far, does it? But nonetheless, it's a very useful move to make in lots of proofs. What we can, because you can do the following. So this is an existential elimination rule. You've got an existentially quantified sentence. You want one that's not existentially quantified so you can get at its internal bits. So we use existential instantiation. We infer that there is some arbitrary thing that satisfies it. So you have to use a variable letter here. I is a variable, not a name. Okay? But that's nonetheless a legitimate inference to make. Say, well, there exists something that's a dog that can read. You say, okay, suppose that's true. There's this thing, Ian, who's a dog that can read. I don't know if Ian's his real name, but let's call him Ian for now. And then you can use that object to make inferences about. Okay? You have to EI to all instances within the of the variable within the scope of the quantifier. So just like with UI, you're not allowed to be selective. E.g., you're allowed to be selective about what you existentially generalize. With UI and EI, you have to do the whole thing. You can't just pick and choose. Okay? And crucially, you're not allowed to EI to a name. This one, I hope, makes perfect sense. So there exists something that is a dog and can read. Does not entail that Adam, my dog, is a dog and Adam can read. Right? That's not what the existential says. That would be fine if it was a universal statement, right? Now, universally, you can stick in a name for, because it's got to be true of every object in the universe. And existential just says there's at least one thing. And when you use existential instantiation, all you're saying is, all right, so whatever that thing is, let's call it I, has got the property, or L and D. But if you use a name, then you're saying this specific thing has these properties, and that's not licensed by the existential. Yeah? Okay. Is it clear why you're not allowed to do this to names? Only variables. Okay. And here's the restriction. This is a really important restriction, and it's going to shape the way that you do derivations from now on. So this is if you've been dozing, now's a good time to perk up. Existential instantiation only works with an arbitrary variable. I'm going to explain in 1 second what an arbitrary variable is. Okay? So you can't do this to any variable. So a variable is arbitrary when it does not appear free in an available line or premise cited in an available line. My way of thinking about this, your variable's got to be fresh. It's got to be unused. It's got to not, basically, if you want to be safe, just use a variable that you haven't seen before anywhere in the proof. What is this A doing here? I'm sorry. I don't know what that is. Okay, it's gone now. Okay. So to existentially instantiate, you have to instantiate to something fresh. Yeah? You can't instantiate to a variable that appears already. Because when you're saying, the move that we made when we existentially instantiated is to say, look, I know that there exists at least one thing that's going to be this. So let's say it's going to be I. Say, okay, I is our thing. You can't know anything about I. So if I say, look, I know there exists at least one thing that is a dog that can read. Well, let's call that thing Corey. So Corey is a dog who can read. No, that wasn't licensed by that existential, right? applying it to some specific thing that you know. Similarly with variables. So if you've got a variable that's not fresh, that we know something about, what you're doing is illegitimately supposing that the existential applies to that thing that you know something about. Right? It's not legitimate to think, well, this is the thing that the existential applies to, because the existential doesn't tell you what it applies to, just that there's one thing at least. Right? Okay. To EI, you gotta EI to an arbitrary variable, a fresh variable that you don't know anything about. Here's why. Okay, the first sentence says, premise one, there is something that is a boy and a dog. Suppose that dogs can be boys. There is something that's good and a ferret. It's premise two. Okay? So now we're just going to EI to I, BI and DI. And then we'll EI again to I, GI and FI. And now we've got the claim that there is something that is a dog and a ferret and good and a boy. Okay? And that can't be right. A dog can be a good boy. A ferret can be a good boy. But ferrets can't be dogs. Those are different things. So what we've done here is the first one was fine. The first one says, okay, suppose there's some random thing. So I is a variable. You say, okay, suppose there's some random thing I. I can tell from the first sentence that there's some random thing I that is both a boy and a dog. Okay, good. And if in the second sentence we'd use J instead, that would have been fine. We'd say, look, okay, the second sentence tells me that there is something that's both good and a ferret. Fine, fine. What we've done, however, is to say, I think those are the same thing. Or not only I think, but like I'm going to assert that those are the same thing. And that assertion of identity just is not contained in those two existential statements, right? So you've given yourself something that you didn't start with. You violated the basic rules of derivations, which is you only get the premises to start with, right? You can only get out of the premises what's already in them. And here we've given ourselves something that's not in the premises. So this is why it's not legitimate to existentially instantiate to a variable that's not fresh, that's not arbitrary. Okay, so this arbitrariness concept is going to be important again on Wednesday because you're also going to need to understand it in order to do universal derivations. On Wednesday, we're going to learn universal derivation, quantifier negation. For universal derivation, you also have to always use an arbitrary variable. Okay. Okay, to review, you must EI to all instances of the variable under the scope of the quantifier. You don't get to pick and choose. You can EI to any arbitrary variable, where arbitrary means something like fresh, unseen, unused before. We don't know anything about this variable. If you use a variable you know something about, what you're saying is, I know which thing is both a dog and a boy. It's this thing from before. And that's something that you don't have just from the existential. So that's the third thing, is just saying the second thing again. You can't EI to a name. Sorry. You also can't EI to a name or a variable that appears already in the proof. Yeah? Sorry, yeah, the second and third thing are basically equivalent. They're just two different ways of saying the same thing. So can't EI to names, and you can't EI to variables. I mean, there are some restrictions. You can EI to a variable that appears boxed in a proof. So it's stuff, you know, if you want to get technical about what arbitrariness means, it does not appear free in an available line. But for the sake of not getting things too complicated, there's enough letters you can always EI to a totally fresh variable. So why not just do that? That's what I would recommend. Just always EI to something. So you should be able to look at the whole derivation and say, I has not appeared anywhere here. That's what I'm going to EI to. Okay. Now, here's why this is super important. Because it's the relationship between EI and UI, right? So you can UI to pretty much anything you want. You got a lot of degrees of freedom on deciding what you're going to UI to. You can UI to different things over and over again. UI is a very open rule, which kind of makes it complicated to use, actually, because you're not going to know, sometimes you're not going to know what the right thing to UI to is going to be. I don't know what I need to UI to. When you're EIing, when you're existentially instantiating, you know exactly what you need to existentially instantiate to. Something fresh, right? Something you've never seen before. And all of those are equally good. So anything that hasn't appeared in the proof before is equally good for you. But you know you can't be clever and like, I'm going to EI to this thing that would be helpful. No, you always have to EI to something you haven't seen before. Now, because you have choice with UI, but no choice with EI, and if you use UI first, you cut off your choice. So if I say, I know what I need. I've got some existentials, I've got some universals. I'm going to existentially instantiate to I, but let me just universally instantiate to I first. Well, now you have I appearing in the proof, right? So I is no longer arbitrary, right? If it's not fresh anymore. If you UI'd to I is not fresh, which means you're not then allowed to EI to it. But if you'd EI'd to I first, then you're allowed to UI to it. So here's the rule. And this is the golden rule. EI first, and then UI to match that. So when you've got an existential statement in the premises or in something that you've derived, you pretty much want to EI to it right away, so that you don't end up later being, I wish I could EI to this variable, but I've already used it, so I can't. Okay? So once we get into the derivations, you'll see the first move you're going to make is EIing and then UIing to match. Okay? Okay. So those are the three rules. Let's take 10 minutes, come back at 11:15, and we'll do some examples. So let's do some derivations. I got 3 examples for you. I only have 3 because I had to pick out ones that work without the 2 rules we're going to learn on Wednesday, and there's actually not that many. So almost all of the derivations you'll see in section 3 require universal derivation and quantifier negation, but these 3 fortunately don't. So let's do them now. Okay. So just to remind you, practically everything that you know about derivations is still the case. So we always start with our show line, of course. We're going to show this existential. Show that there exists some x such that fx, or gx than fx. Yeah? Okay. You can't, so in general, I'm going to write this line out. It's not going to help us right now because we don't have quantifier negation yet. In general, you're still going to do the thing where you say, okay, well, I want to show this, and it's not conditional, and it's not, in this case, a universal. So I'll just assume ID, so there does not exist x, gx, then fx. So fine for assume ID. Again, that's not going to help us here, but we'll do it anyway.
Can't you just go for every g of x and not fx?
No. You're not allowed. So she's asking, can I do the following? There exists an x, gx, then not fx?
No, for every x. So
Oh, I see. Can we just say the following for all x,
g of x and
gx and not fx? No. Even that is not. So what you're doing is using quantifier negation. Yeah? So what you're saying is for all x, not gx then fx. Okay, we don't have that rule yet, basically. We're gonna learn that rule on Wednesday, so we're not gonna do that yet. Okay? Okay. So if that was like, hey, what's going on? We'll talk about it Wednesday. Okay. So we're trying to show there exists an x such that gx then fx. Now, what have we got? We've got this negated existential, which I told you is no good to us, and we've got this existential statement as a premise. Okay? Now, remember what we just said at the end of the last section here, where he said, the thing to do, if you have an existential, the thing to do is do your existential instantiation as soon as you can. Do not delay. Get it existentially instantiated right away. So that's what we're going to do right off the bat. And a fresh variable is I, so that's premise 1 E I. Okay? Okay. Now, the thing that we're trying to get is itself an existential statement. How do you get an existential? Yeah. You EG to it. Right. Exactly. So what we want is to have a version. So this says there exists something such that if G is true of X, then F is true of it. So what we want is an instance of that. We want something that we can use to existentially generalize to this. Okay? So what we want is the following. And given that we've got Fi, what we want is to show if Gi, then Fi. Yeah? We want to show that. That's what we want, because what we want is to be able to existentially generalize to the conclusion there. Yeah? Does that make sense strategy-wise, what we're trying to get to here? Sorry? Right. So the thing that we want is, of course, the conclusion. The way to get an existential is to show a version of it and then existentially generalize. Right? So that was the introduction rule. To go from not having an existential statement to having an existential statement, the rule we use is existential generalize. It's called the introduction rule for the existential. So to introduce the existential, we need to existentially generalize. To use that rule, what we need is an instance of that thing that we can generalize from. So to get an instance of there exists an x such that gx then fx, then all we need, so anything, if we had a named thing, ga then fa, that would be great. Right? We could existentially generalize that, no problem. If you have this, then you can infer there exists something such that gx then fx, right? We don't have any names available here, so there's nothing specific that's been named, so we're not going to be able to do that. What we've got is fi. So all we've been given really to work with is this thing, and all we can do with that is existentially instantiate, and you do that right away. That's kind of an automatic move, right? Do that right away. You don't even know how you're going to use it, but you do know you want it done right off the top. So good. We've existentially instantiated to I, and that means that the version of this that we're going to try to build is if gi, then fi. So that's how we got to there. Okay? Okay. Now, of course, we can do our just usual. We're going to assume this for conditional derivation. Now we need to show fi somehow. We're going to rack our brains trying to show fi. Well, we've got fi, of course, from line 3. And on line 7, we've got a direct derivation. Yeah? Which means on line 6, we did our conditional derivation. It's all just good old-fashioned sentential logic. Yeah? Yeah?
Would it have also been correct to use the addition rule on line 3 and say not GI or
Yeah, that would have been fine. Yeah, that would have been fine. Wait, addition, not GI or FI. Yeah, I think that would have worked. Yeah. Okay. Yeah.
Why did you need to show FI one record
Just right here, you could just repeat line 3. Because I always write these show lines. This is just a...
would it still be correct if you just repeated like you said like line 3?
I think I required that you always write the second show line. I think that's what I said. Wasn't it? I believe it is. I believe it is. Okay, yeah. Yes, then yes. That is, I mean, that is what I said, that I do want you to write that second show line. Yeah. Okay. So, now we've got our instance. We've got that thing that we said we wanted to existentially generalize over, right? So now we just write out there exists an x such that if gx, then fx, and that is line 4 ei. And that's it. That's our line 10 direct derivation. Yes, absolutely it would be EG instead of EI. Thank you. Line 10, direct derivation. Yeah?
Can we see what the suggestion or the other way of deriving it was? Because it wasn't said that you like add,
Sure, sure.
but if you're adding, don't you get a conjunction and then you can't use CV to it?
No, you can't. So you adjoin to get a conjunction, not add. So the suggestion was we do not GI or FI with addition, right? Line 3 add, yeah? And then what?
Oh, then CBJ it, so GI, then if GI, then FI.
FI, good.
And then EG.
And then EG. Good. More efficient. That is an existential generalization, not an existential instantiation, as some people would have you believe. Okay. There we go. So that was the suggestion. Yeah. Yeah.
I'm confused with EG because isn't X already a new variable? Do we have to instantiate a new variable EG?
No, no. That's the requirement on EI and UI. Or no, sorry, on EI. The freshness of the variable. So with EG, you're not allowed to do one that's already contained in the sentence. That was the no capturing rule. With EI, it's got to be something totally fresh. But EG, you can existentially generalize to an already used variable. That's OK. All right. Yeah.
Did you pick GI instead of FI, or does it have to be?
So you're not. So you can't get. We got FI because in this premise we had there exists an x such that fx. So that's how we got this FI. We didn't just sort of.
Arbitrarily just use the variable inside the.
So yeah, we didn't just pick our own predicate. We just slotted in an arbitrary variable for that. Yeah. Yeah. I'm seeing shaking of heads with disgust and horror. Okay, want to do another? Oh, let's do another. That was so much fun. Jeez, all right. Come on, it's fun stuff. Okay. Show if FA, then there exists some x such that gx and hx. Good. Okay. So your good old-fashioned sentential logic skills all still apply. So when you're looking at a show line that is a conditional, you start a conditional derivation. That's the move, right? If it was just the existential, then we'd have to think harder. If it was a universal, we'd have to do the thing we're going to learn on Wednesday. But if it's a conditional, you start a conditional derivation. So what we're going to do, we're going to assume the antecedent for conditional derivation and try to show the consequent. Okay. Again, because we haven't got quantifier negation yet, it's not really all that useful to start and assume ID, but I'll do it just for the sake of being consistent. When you're out of options, you assume ID. Okay. Okay. Now let's survey what we've got, see what we can do. So far what we've got is line 2. We've got FA. That's something. We've got these premises. For all x if fx and gx, and for all x if gx and hx. Okay. So very few restrictions on what we can do with those is universally instantiate them, right? So a universal is a really nice thing to have as a premise because you can pull out a bunch of unquantified sentences from it as often as you like, as many times as you like, as many different things as you like. You can keep pulling stuff out of them. You do have to, however, figure out what you want to pull out of the universal. You don't just start pulling stuff at random because you're just going to, waste paper or whatever. So you UI to something that'll be useful to you. You UI to something that matches something that you're likely going to find helpful. Okay, and
Is it necessary to UI this derivation?
is it strictly speaking necessary? I don't know. The way I solved it, it is. Is there a way of not UIing?
I think so.
Yeah? Okay.
I just used f of a, and then if you apply f of a to PR1, then you get g of a.
Nope. Nope.
Doesn't that make sense?
So the suggestion was that we use line 2 and apply it to premise 1, but you're not allowed to do that. So you're not allowed to say FA and this thing modus ponens.
Well, isn't that first line saying that for every x, you get any half of x, you get
That is what it's saying. But what we have to do, in order to be able to apply the rule modus ponens, you need something that's a conditional. And this is not a conditional. This is a universally quantified sentence. So the main operator is this for all x, and you're only allowed to apply our rules to the main operator of the sentence. That's right. So what we have to do, your suggestion is exactly right. It's just you need 2 steps to do it. So what we need is to universally instantiate premise 1. Premise 1 UI. So basically, you're just thinking 2 steps ahead here. So we got to do it. We'll do it step by step. So we're going to UI premise 1, and what are we going to UI premise 1 to? To A. To A is the only thing that has appeared. That's the only reasonable thing that's appeared in our proof so far, right? So we've got now if FA, then GA. Yeah? So that's cool. That's helpful, right? Because now we can we'll just do the automatic move. Like we've got FA and we've got if FA then GA, so we'll get ourselves GA. So line 2, line 5, modus ponens. Cool. Now what? Oh, thank you. Okay. Well, G appears somewhere else in our proof. Actually, G appears several places. So now, This is another thing that you might want to UI to, right? Or from. So let's do that. Premise 2, PR2 UI. That gives us, once again, we'll do it to A to match. And now we get ourselves HA from 6, 7 modus ponens. Yeah? Okay. Now it's time to remember what it is we're just moving on automatic moves here. Now it's time to remember what we were trying to accomplish. What we were trying to accomplish was to show this existential. There exists an x such that gx and hx. So all we need to get that, right, this just says there's at least one thing in the universe that's got property gx, or got property g and got property h. We've got that, right? We've got enough stuff to build that up. We've got that A has property G, and we've got A has property H. Great. Now, you can't just, so here's what you're not allowed to do. You're not allowed to just say line 6, line 8, EG, because EG only takes one input. So we just got to put it together as a whole sentence. What you need to do is build yourself an exact match of this. An exact match of this. So we need GA and HA from line 6 and line 8, ADJ. Yeah? Okay? And then we existentially generalize. We say, given that I know that A's got both property G and H, oh, not EA, there exists an X such that GX and HX. Line 9, E, G. Great. And once again, I'm writing the same number twice. OK. So that means that on line 10, we did a direct derivation. Closing off this show line. We got the thing. We were trying to show this thing. We got the thing. Hooray. Line 12, we did on line 3, we did our conditional derivation. Box and cancel. Yeah? OK, so this one weaves in more of our good old-fashioned sentential logic skills, but it's the same basic idea. Right? You want an existential. The strategy is, so in this case, it wasn't the first thing we wanted. We wanted to do this conditional derivation. But once we start the conditional derivation, the thing that we want is this existential. And to get an existential, you need to existentially generalize from something that matches this nicely. So we needed something, G of blank and H of blank. And because we had FA, that was a handy thing to UI to, right? You UI to whatever you've got, whatever it looks like is going to be useful. And that's how we built GA and HA, existentially generalize, and we're done. Yeah? OK. Let's do one more. Unless there's questions about this? OK, let's do one more. A theorem. This is from the textbook. OK. So we're going to show this big funky thing. X, GX, then OK. Can you intuitively see why this thing should be a theorem? If for So the antecedent is this universally quantified, this is a conditional, right? You see that the main connective here is this conditional. So it's saying if this thing is true, then this thing has got to be true. If for all x, if x has property f, then it has property g. If all f's are g's, then if there exists something that's an f, there must exist something that's a g. Intuitively, that makes sense, right? Yeah.
Why do you have two existential generalizers or quantifiers in the consequent? Why isn't it just one outside the bracket, one to both?
In fact, I mean, so the question is, why can't we do the following? There exists an x, sorry. These are actually slightly different sentences. Because the scope of this, recall the scope stuff? The scope of this is just this sentence. The scope of this is just this sentence. So the scope of this is this whole sentence, which says that it's the same x. But this is not actually claiming that these are the same x.
Right, but I guess part of what I'm confused is it seems like them being the same x is what follows from the consequent.
Well, that's a slightly stronger implication. So you can also get that they're the same x, but this is a weaker claim, that if there's anything at all that's an x, or that's an f, there's got to be something that's a g. Yeah? And that's true, right? So
But don't you get that they're the same f from the consequent?
you could. Well, no, so this is the consequent here does not claim that they're the same object, even though you could claim that. So the antecedent has it being the same thing. So for anything, if this thing has the property f, then the same object has the property g, because the scope of this is this whole sentence. Now, this is making a weaker claim. It's saying, look, if there's anything at all in the universe that's an f, there's got to be some random thing in the universe that's a g. Not necessarily that they have to be the same thing, but it's still, I mean, it's possible. There's nothing that rules out that they're the same thing. Does that make sense? Okay. So he's just asking, why isn't the consequent making a stronger claim here? And the answer is no reason. That's just the thing we're trying to derive. Okay? Okay. So let us begin. Okay, so what do we say this thing is again? Conditional. So we start a conditional derivation. So we're going to assume the antecedent, as always. Assume if fx, then gx. Assume for CD. And we're going to try to show the consequent. That if there exists something, fx, then there exists something, gx. Okay. Now, what is this thing we're trying to show now? It's another conditional. So we start another conditional derivation. So assume there exists some x such that fx. Try to show there exists an x such that gx. Okay. And why not? Let's do the assume ID. This will be a useful move very shortly, but right now it's not going to help us much. Okay. All right, so we survey our resources, see what we've got available, see what moves are obvious, are automatic. Well, what do we got? Oh, boy. All right. Well, we got a universal on line 2. That's helpful. That'll be good. We've got an existential on line 4. Very helpful. We've got a negated existential on line 6. Just today, that's not useful. As of Wednesday, that will be useful. But so far, this is no good to us. All right. So we got basically, that's all we've got. We've got a universal, and we've got an existential. And what do we always do when you have those two things? Do we start randomly UIing to things, hoping something works out? No. We EI first. You EI to some fresh variable such that you've got it. You've drawn something out of your existential So f, we'll call it j this time, just for variety's sake. So I know that's why you come to these logic classes, variety. Okay. For existentially instantiated, line 4. Cool. Okay. So now that we've existentially instantiated to j, that's the thing to match, right? If we're going to do for example, the only other resource we've got here is this 2. So we might as well universally instantiate this to match the thing that we existentially instantiate it to, right? So maybe it'll, I don't know. I haven't even started thinking about, so far all we've been doing is the automatic, oh, it's a conditional derivation. Oh, it's a conditional derivation. Oh, I have an existentially instantiate. So these are all just perfectly automatic moves so far. So all x, fx, then gx, good. So what I'm going to do is say, if fj, then gj, which is line 2, ui. And why do I, that's like the 5th time today. Okay. All right. Yeah, so and now I'll just give myself gj. Cool. All right. Because I've got line 7 and line 8, modus ponens. Okay, now I take a breath. I've got my automatic, I've just been on autopilot so far, being like, automatic moves, automatic moves, automatic moves. The existentially instantiate is an automatic move. Matching, it's not necessary, you don't have to necessarily do that off the bat, but it's almost always a good idea if you've got a universal to match something you've got. Now I have to start thinking again. Now I have to go to my most recent show line and be like, what was I trying to show? What was I doing again? Oh yeah, I'm trying to show that there exists some x such that gx. Well, bully for me, I've done it. There exists some thing that has the property g. Yeah? So now we, e.g., we say line 9, e.g., and we get that there exists some x such that gx. And we've shown on line 10 the thing we were trying to show by direct derivation. Okay. Draw a line, Corey. You can do it. Okay. Good. So we showed the consequence in this conditional derivation on the assumption that there exists an x such that fx. My x's are bad, but that's okay. So on line 5, we did a conditional derivation. Hooray. And then on line 3, we did a conditional derivation. Ta-da. We have done it. Okay. Okay, predicate logic derivations. There they are. So as I said, we've got 2 more rules to learn on Wednesday before you're ready to tackle any of the exercise questions. I believe all of the exercise questions involve. So what I've shown you today is how to pull something out of an existential with existential instantiation, how to pull something out of a universal with universal instantiation, and how to build an existential with existential generalization. Wednesday, we're going to learn how to build a universal using universal derivations and how to flip between existentials and universals using quantifier negations. Okay? Yeah? The last derivation from the test? I don't have it with me, and I don't think that there's actually time, unfortunately. Okay. I'll post it on the Quarkus. Okay. All right. Thanks, everyone.